AR4-087. This event caused significant radio blackouts across Europe, Asia, and the Middle East, highlighting the profound impact solar activity can have on our technology-dependent world. The X 2.7 class solar flare that erupted on May 14, 2025, stands as the most intense solar event of the year. Originating from sunspot region AR 4087, this flare peaked at 0825 UTC, releasing a massive burst of energy that traveled at the speed of light, impacting Earth's upper atmosphere almost instantaneously. Solar flares are categorized based on their X-ray brightness in the wavelength range of 1 to 8 angstroms. The classes A, B, C, M, and X represent increasing orders of magnitude, with each class being 10 times more powerful than the previous. An X-class flare, therefore, is the most potent, and the number following the class indicates its strength. An X 2.7 flare is thus 2.7 times more intense than an X 1.0 flare. Sunspot region AR 4087 had already shown signs of heightened activity prior to this event. On May 13th, it produced an X 1.2 class flare, followed by an M 5.3 class flare earlier on May 14th. These successive flares indicate a highly active region on the sun's surface, capable of producing significant solar storms. The X 2.7 flare's rapid release of X-rays and extreme ultraviolet radiation ionize the Earth's upper atmosphere, particularly affecting the ionosphere's D layer. This sudden ionization disrupted high-frequency HF radio communications on the sunlit side of the planet, leading to widespread radio blackouts. While the flare itself did not produce a coronal mass ejection, CME, directed at Earth, the potential for future CMEs from active region 4087 remains a concern. As this sunspot region rotates to face Earth more directly, the likelihood of Earth-directed CMEs increases, which could have more severe geomagnetic consequences. The immediate aftermath of the X 2.7 solar flare was felt across multiple continents. High-frequency radio blackouts were reported in Europe, Asia, and the Middle East, affecting aviation, maritime operations, and emergency communications. These disruptions underscore the vulnerability of our communication systems to space weather events. The flare's impact on the ionosphere led to increased absorption of HF radio waves, particularly in the 3 to 30 MHz range. This absorption rendered HF radio communication unreliable or completely inoperative in affected regions, posing challenges for industries and services that rely on these frequencies for long-distance communication. Beyond communication disruptions, solar flares can affect satellite operations and navigation systems. Increased ionization can lead to signal delays or loss in global navigation satellite systems, GNSS, impacting GPS accuracy. Satellites in low Earth orbit may also experience increased drag due to atmospheric expansion, potentially altering their trajectories. While the May 14th flare did not produce a significant CME, the potential for future CMEs from active region 4087 remains. CMEs can induce geomagnetic storms upon interacting with Earth's magnetic field, leading to power grid failures, pipeline corrosion, and increased radiation exposure for high-altitude flights and astronauts. The cumulative effect of these disruptions highlights the importance of monitoring solar activity and developing resilient infrastructure to mitigate the impacts of space weather events. The recent solar flare activity is a stark reminder of the sun's immense power and its unpredictable influence on our technologically dependent world. As we edge closer to the peak of solar cycle 25, expected sometime around late 2025, scientists are closely monitoring a sharp uptick in the frequency and intensity of solar eruptions. These flares, especially of the X-class variety, are becoming more common and impactful. Over the last 2 years, the Sun has been particularly restless, providing a dramatic prelude to the